And so from an admin perspective, I do want to talk about, I have 6 notes here that I want to talk about. So one no quiz this week, right? So I moved that. I think I moved one. There's only 2 quizzes left for the quarter. So no quiz this weekend. I posted an updated schedule on Teams, right? So it's in the chat that just sort of has the day-by-day breakout. And I'll try to update the Excel spreadsheet on Canvas this weekend. And I have 2 lofty goals this weekend. One is in terms of grading, and I would like to get homework 4 in the midterm graded over the weekend. That's a goal, okay? So we'll see how that goes. And I want to have homework 5 posted on probably Sunday evening for that. So that's what I'm going to try to do. The bigger one is this GPOPs tutorial that I wanted to do this upcoming week. And so today, I think today's lecture, and these are like famous last words, I think today's lecture, I want to keep it short. So I want to try to keep it short, but we'll see what happens. But it's going to be covering direct collocation methods or collocation methods, depending on how you pronounce it and or spell it correctly or incorrectly. And that's a natural segue into some more state-of-the-art direct orthogonal collocation methods, i.e. we'll talk about pseudospectral methods, which is a great segue into talking about GPOPs 2, okay? And you know, some of the other software that we have on here, like Dido, and whatever else is on there, right? SOS, SOX, or those are more just direct collocation methods, right? So I had 2 ideas I want to throw out, because you're welcome to use GPOPs on the final project, okay? I'm not saying like thou shalt use GPOPs, but you are more than welcome to use it. So I thought either two scenarios. One Thursday afternoon, and it would probably be around like lunchtime, right? Maybe like a 12 to 2, because it needs to be, I think, about usually 2 hours is what it ends up being, because I'll do the first hour kind of reviewing a top level pseudospectral methods and GPOPs, and I'll try not to get into whether or not some people consider GPOPs a pseudospectral method or not. That's just nerdy in the weeds drama. And I do like a summary of it, okay, and talk about how to set up the problem and everything, and some tips, and talk about keep out zones and super quadrics, and I introduce some interesting, in my opinion, and great topics that could be useful. And then the second half, we kind of sit down together, and it's actually might be easier doing it virtually versus me standing up and talking through an example, but where we'll code up a couple things from scratch, right? I'm probably a double integrator. And you know, maybe since we have a good initial guess for the Dubinskar, so we could do taking a closed form solution from the midterm and using that as the initial guess to solve for the Dubinskar problem in GPOPs. So the other option was doing that Wednesday instead of a lecture. Okay, so it would be maybe an extended lecture, if that makes sense. So maybe from 4 to 6, because I think, you know, people have class before this. You know, so I just want to put that up to you all when would be best for you. That said, right, I would make Friday's lecture next week kind of optional, and we would just sort of review current optimal control research that we've done here at AFID. Usually Dr. Cobb gives that lecture. I haven't talked to him about it this quarter yet, so I'll probably just do it if he's not available. It just sort of snuck up on us for this one. So. Any thoughts on that, or any preferences to whether it's options being Wednesday 4 to 6, which I understand it's getting kind of late, or Thursday noon to 2, or 1 to 3. The only reason I'm saying that noon to 2, maybe like a 12:30 to 2:30 is just because I have a meeting regularly at 3, the OEM stuff. So any thoughts from anybody?
I prefer the Thursday in general, but I'm good for either time slot.
Okay.
Same. I prefer Wednesday, but I'm the only one so far, sounds like.
Throw my vote in for Wednesday. I could go either way, but I'd prefer Wednesday because Thursday's supposed to be my husband's day in the office. So otherwise, it's going to be lots of movie time here.
Okay. Yeah. So it sounds like maybe kind of preference towards Wednesday. Anybody feel super strongly against Wednesday? Anybody really excited about Wednesday as an option? Okay, so Paul has his hand up. Paul, is that a question hand or is that a excited hand?
I'm thrilled for Wednesday.
Okay, cool. All right, good. So 1 out of 12 people in the class is thrilled for Wednesday. Sounds like a majority, so we'll go with that. Okay, and it should be good, right? So that means for Wednesday, just make sure if you want to follow along, right? And so granted, if you don't want to use GPOPs, then there's probably no point. I mean, it'd be good for your awareness, right? But if you're not going to use GPOPs, come into a GPOPs tutorial, maybe not the best use time. So that last half, you may not be interested in. But I think it would be pretty useful. And it will also talk about how to implement like keep out zones, and there's a couple other really unique topics that I cover in there towards the end. Oh, and debugging, right? You could spend the past 5 or 6 years using GPOPs and never knew there was a debug command. And so we'll talk about that and how to make your life a lot easier with it. Okay, so any admin questions or anything else to cover? And so I will say, right, the next Monday and Tuesday's lecture, right? So I would say maybe look at some of the material. It's basically a slide deck that we're going off of from a short course on pseudospectral methods, and maybe some material from ACES 771A. But it's going to be probably a lot of stuff that we've never seen before, and we're going to put it all together to try to solve really hard optimal control problems. Okay, so I don't expect you to immediately process everything. I still don't process a lot of the mesh refinement stuff, but I just want you to be aware of the terms that we're going to start using right when we try to solve these problems, because it turns out these numerical methods we can generalize instead of having to go back to indirect methods and come up with our necessary conditions and do all the stuff we've been doing for the first half of the class. Okay, and so that's a kind of a good segue into today's lecture, right? Which hopefully, can you all see the slides right now?
Yep.
Yes, sir.
Yes, sir.
Okay, cool. So today's sort of an introduction into direct collocation methods, and I'll probably switch whether or not I'm saying collocation or collocation, just based on what I think is the right way to say it at the time, and you'll hear people pronounce it differently, and you'll also hear it, well, see it. You don't hear things spelled, but you'll see it spelled differently. This 2 L's is the correct way, I'm pretty sure. I wouldn't have it in the title if it were the wrong way to spell it. But what do you think we're talking about when we say direct collocation methods? Has anybody heard that term before?
Yes, sir. Is it like directly numerically solving for something?
Yeah, so the direct part of that is where we're directly solving that approximation of our optimal control problem. The collocation part is the interesting part of this, right? So what were we doing with shooting methods in terms of, let's say, the state dynamics?
We would project it forward from an initial guess and then figure out our error and then project back.
So we would shoot it forward and we would propagate it forward, okay? But how were we propagating forward in time? Or backward in time? Some kind of numerical integration, or we had a state transition matrix, right? Okay, so here we're not really going to integrate the dynamics. Okay, what we're going to do is we're going to approximate that integration and come up with a series of these things called defects. Okay, so in general, a priori, we don't necessarily know the structure of the optimal control problem that we're about to solve. Okay, so what does that bullet mean? Or what does that statement say? We don't necessarily know the structure of the problem. I'm
You
trying
don't
to
have
figure out.
like an initial idea of what the structure is?
Yeah, so I guess that kind of depends on what we mean by the word structure. Okay, so in this one, it's saying we don't know the structure. Let's say we don't know the structure of the actual optimal control profile. Okay, so we don't know whether that's going to be the sum of a quadratic plus the sum of a cubic, or it's going to be the arctangent of some polynomial plus the arctangent of some polynomial. But if we think about what we did in direct shooting methods, we parameterized the control. Okay, so with collocation methods, we're going to parameterize both the state and the control, and it's going to allow us a lot of flexibility when we go into solving problems that have multiple phases, and especially when we have path constraints. So something that we haven't talked about before is when we have path constraints. Okay, and I'm going to see if I'll just do like a general kind of discussion on here, right? So back in the day, right, when we appended our cost function, right, we had J, I don't know, like, seems too aggressive. So back in the day, when we appended our cost function with a convenient form of 0, right, we basically said that J was an integral from T0 to TF, open some brackets, we've got our running costs, right, as a function of X, U, and T. We had a convenient form of 0 that we added, right, lambda transpose of T times X dot minus F. I could add another convenient form of 0, okay, that would be another adjoint, another set of adjoint variables, okay, like a mu transpose of T. And I can multiply that by, let's say, some path constraints, J of X and T, okay, dt, where I'm just saying that J of X and T is equal to 0, right? And so similar to what I was doing with the co-states, right, I just have another set of adjoint variables here, okay, that I would also need to solve for, and I would need to come up with my necessary conditions, and we didn't do that for this problem, okay, because that's really hard to do, okay. So these would be like some auxiliary Lagrange multipliers, or these would be, you tend to see the term adjoint variables, okay, in this case, associated with the path constraints. So here you have adjoints associated with state constraints, the state dynamics, and here you have adjoints that are associated with the path constraints. And maybe that's a path constraint that's saying if you're a bead like rolling along a surface, okay, maybe you have a path constraint that says what that surface is. There's a pretty classic benchmark problem that talks about is it Arnold Palmer, the golfer? Yeah, and so it's a golfer and it's a paraboloid, right? And you're trying to figure out the trajectory to go from the hitting of the golf ball with the club. Yeah, that's what you call it. But you're trying to figure out the trajectory of that, and you're trying to get it into the I wanted to say the hole, or the do we have a term for what the
green?
Oh, yeah, like a hole in one kind of thing, right?
The
So
green.
but you're putting it, right? So but it's putting, right? So you're not doing the initial that. So you're like trying to figure out the trajectory that gets there in min time or something like that, right? And so there's a lot of problems with how that problem was initially formulated, because when you go through dynamics, it's something about how the center of gravity of the ball, when you look at the constraint, it disagrees with, they contradict each other. But that's and so I would look that up if you're interested. But that's telling you that there's a path constraint that you need to stay on the surface of that paraboloid. There's another problem called the alpine skier, right? Which is, it's a skier that's trying to ski, right, through the Alps. And they're being modeled, right, as hills and valleys, right? So at any point in time, because you're going to assume that you're not going to do any jumps or anything, you need to stay on that surface, okay? So that's a hard problem to solve, right, with that. Okay, so that'd be an idea of some other things. You might also have constraints that are, or path constraints that are inequalities, okay? So, Jacob, I'll go to you for, since you're doing a reentry problem, can you think of any inequality constraints you might have throughout your trajectory that your vehicle would have to, thou shalt be less than or equal to this?
Yeah, for sure. That'd be heating constraints, right? How much heating the vehicle can take, as well as loading. How many G's can it take?
Yeah, right. Yeah, and there's probably a whole bunch of others too. But so that'd be an example of like an inequality path constraint. Okay, and so those are really hard to come up with solutions for analytically with indirect methods. Are they hard to get solutions for with direct methods? Yes, but can we do them? Yes. Okay, so this allows us for flexibility on multiple phases of the problem and adding in path constraints in the problem, and we get better accuracy than shooting methods. Okay, and maybe better conversions too. Okay. So we're not propagating the dynamics with collocation methods, but instead we're really creating constraints, and they're going to be algebraic constraints. And those algebraic constraints, they're created from the differential equations, okay? And it's going to be depending on what type of method that we use for the collocation, okay? So in the references for, if I have time at the end, which I really wanted this to be a short lesson because it's Friday and it's been a week. But towards the end, there's this really great paper by Matthew Kelly that walks through how to do, it's like do-it-yourself collocation methods. And it's really cool, and it's in the references for this one. And there's a lot of example code where you can pick the type of numerical integration that you're doing, right? So you might choose to do trapezoidal, and we kind of talk about this when we introduce numerical methods. You might do trapezoidal, you might do Hermite-Simpson, right? You might do a Runge-Kutta, and there's a difference between if you're doing this with implicit or explicit methods. But you can come up with algebraic constraints that your states have to abide by, okay? And so you can essentially turn those into constraints, right? So I just said that you can turn constraints into constraints. We're going to come up with algebraic equations, okay, based on the numerical integration scheme that we can turn into constraints, okay? And that's going to eventually lead to a really large nonlinear program. We're saying nonlinear program in general because it probably will have some nonlinear terms in this, right? You could probably turn this into, you could probably maybe transform and make some assumptions or linearize it into different types of programs, but instead we're just going to say at top level on NLP, okay? Where we want to minimize an objective function subject to equality and inequality constraints, which if we go, you know, if we just circle back to the very beginning of the quarter, that's exactly what we were doing. Okay, except maybe they weren't going to be as large of NLPs. And so here's an example. And I switched back from the whiteboard to the slides. Can you all see the slides?
Yes.
Yeah.
Yep. Thank you. So this says on the midterm. So there used to be a problem on the midterm where we did this. So that's sort of a relic of the past. But that's the example where we approximated the state in the LQR satellite pointing problem. If you remember from a couple weeks ago, where we did x to k plus 1, what was my current state plus some time step, right? Some delta times my dynamics, right? Do you all remember doing that with the sort of scalar LQR example? Okay, so we definitely did it, right? But let's just pretend that we did, right? So we're going to approximate the state with these dynamics. So like a simple like Euler forward integration scheme, okay? And so you can sequence that forward, right? So hopefully this looks familiar, where I can go all the way to x sub m, right, with x sub m minus 1, okay, plus that same step. And this would be an example where we're using the same h, the same delta between t. So this h here might be tk minus, or tk plus 1 minus tk or something like that. But I can take this left-hand side, and I'm saying it equals the right-hand side. So what I can do is I can turn left-hand side minus right-hand side, set that equal to 0. So now instead of a series of propagations or sequencing forward, I have what looks like a set of equations, right? Or I have what looks like a set of equality constraints, okay? And you tend to see this called a defect, okay? And what you want to do is you want to minimize your defects, okay? So what are your design variables? Well, maybe it's going to be your x's and your u's in this case, right? So we're adding more unknowns to the problem, and you know it could be this situation where, in this case, if you pick a t0, you're going to know your actual values of tk and tk plus 1.
You mentioned wanting to minimize defects. Is that minimizing the number of defects or the equations themselves?
So the equations themselves, right? And there will be different ways to solve this. So these defects are going to be your equality constraints for the most part. Okay, that's not the only thing that we want to minimize, though, in this problem, right? Because these are just the dynamics that our system is supposed to obey. Okay, so maybe these are like defects in the dynamics or something like that, right? And you can satisfy that in your equality constraints for the most part. What you may want to minimize, and Paul, did that answer your question?
Yes.
Okay, but what we do want to minimize is probably this integral. Okay, and so we had like this approximation of this integral of a constant time step, right, where this was equal to the sum over all those time steps. Okay, so does anybody remember what we called approximating a definite integral? And it started with a Q.
Quadrature.
Yeah, so this is like a really simple, not an awesome way to do quadrature, and we'll talk about why later, probably early next week. Okay, but for the problem that we were doing, it was a really quick and easy problem to solve, so we can make h really small, and this ended up not being bad. But in certain problems, right, if you make h really, really small, you tend to have some issues right on the extremes. Okay, so, and also based on the degree of polynomial that you're trying to approximate something as, right, if you keep increasing that order of degree, the more and more error you're going to have for that. And we'll talk about that on Monday and Tuesday. We could also add a terminal cost. And one thing that we didn't cover in terms of terminal cost, and I think it is worth saying, right, is I can go between the Meyer form and Lagrange form. Okay, and one thing I didn't cover was if I go from the Lagrange form to the Meyer form, I kind of have to add an additional state. Okay, so I could go to something that looks like, let's say I've got something that looks like J is an integral from T0 to TF, just L of x, u, and t dt. Now, I could go to something, and let's say this is x dot equals f of x and u, or something like that, right? I could turn this into the Meyer form, right, where, I use my, maybe I do my calculus, I do my fundamental theorem of calculus, right, and I move this over here, and I turn that into a terminal cost. Because, if this were v, I could put v dot in here, right? So maybe this is like an integral of that or something. But what I kind of have to do also is I need to keep track of that running cost. So I could add an x sub n plus 1 dot is equal to L of x, u, and t. And I would have that x n plus 1 at 0 is equal to 0. So if I do that, right, I might have to add an additional state. Okay, and so that was just sort of, I didn't actually mention that, but I need to keep track of that running cost if I do that. But it ends up being a different, so it ends up being, the cost function will kind of the same, but it ends up being a different solution process. And maybe it's not the best way to go about solving this, right, in this day and age. Back to lesson 26. So we can add in a terminal cost. Okay, so we've got this J, and that's in the Bolzano form, right? Because we've got both a terminal cost and a running cost. And we have boundary conditions, okay, which I could then turn those into inequality constraints. Okay, so I'm going to say minimize this f of z. This could be something with an approximation of this terminal cost right here. And I'm subject to some equality constraints, and that doesn't necessarily have to be the number of my dynamics. That could also include my boundary conditions in there. Okay, and so now we just need to go about trying to solve this large nonlinear program where our design variables are x naught through xn and u naught through un minus 1. And there's going to be a discussion that we have on Monday about when we do this, about do we include the boundary points, okay, of the mesh or of the discretization, okay? And we're going to have basically 3 different ways to do that, where we include both boundary points, one or the other, left or right boundary point, and no boundary points, okay? And that can influence the accuracy of some quadrature with that. Okay, So with that Euler forward, essentially, as you increase that number of intervals, your number of NLP variables kind of increases by 2n, okay? And if you've got n states and m controls, you've got about n times n plus m variables. So you can end up with thousands of variables pretty quick, right? If you have 100 variables and you just have 5 states and 5 controls, or let's say you have 6 states and 3 controls, 100 intervals, that's 900 variables basically, right, that you're solving for. So they can become very large. But if you look at the structure of the matrix, like if you were able to turn this into a matrix times design variable equals something, you could get this matrix to look really, have a really nice structure, and it could be sparse, and you could exploit that sparsity, okay? So sparse maybe means I've got, 100 by 100 matrix, right? And maybe it just looks like blocks of 2 by 2 matrices all the way along the diagonal. That would be a sparse matrix, right? And there are different ways we can, and there are built-in sparsity related functions in MATLAB that we could use if we were going to do this ourselves. We don't have to do this ourselves, but we can talk about it, right? But these collocation methods, they tend to yield like large, sparse NLPs, okay? But there's a lot of solvers already out there, like SNOP, for example, to do that. So in general, when you're doing a collocation, you want to split your segment up into various time segments. Okay, so this would be like time 0, time 1, time 2. And doing this in the terms of the absolute time, i.e. going from 0 to 100 seconds or 100 minutes, that's probably not the best way to do it in terms of scaling the problem. Okay, so we may want to do some type of transformation on that time, right, in order to get everything maybe on the same order, because that really helps us in the solver. So if you look at any segment T sub k and T sub k plus 1, your state and your control over these, you're not shooting there anymore. You're replacing these by algebraic expressions. And why is this? Is because this is a direct method, okay, that we're not coming up with an analytical solution for the problem, but we are coming up with an approximation of the optimal control problem at a series of points. And you're kind of collocating that time to this point. And I'd be interested if you go out, if you're out, if you go out over the weekend, right? If you Google over the weekend, what does collocation mean, where that term collocation comes from? And if you find out, please share it with us, right? The answer to that. So your constraints could have these forms, right? So here, these were your defects, okay? And you've got some kind of constraint vector in general. And here, this would be C lower and C upper. And this is using notation out of Betz's paper, right? His survey numerical methods, and also Betz's text, right? And this is a really good text. I don't know if there's a PDF of it available, but it's this practical methods for optimal control and estimation using nonlinear programming. It's pretty good. There may or may not be a PDF of it, but his paper does a really good job of summarizing it in there. This just walks through some really good examples that we can look at. Now, I'll try to take one of them and try and do a case study of. Betz is also the author of that collection of benchmark test problems. That he's just done a lot of work in this field. He's a aerospace guy, right? No, Boeing. He's a Boeing guy. Yep. Was he both? Boeing guy.
Sir, can I ask a quick question?
Yeah.
So if you're trying to minimize the number of defects that you have, is there any concern for any loss of state information?
Yeah. Okay. So we're not really minimizing the amount of defects, right? So we're not minimizing the number of defects. We're counting those defects.
Yes. That with the equations themselves.
Yeah. Exactly. And that's a really good point in terms of, are we losing information on the dynamics? Okay. And the answer is maybe. Okay. Because we're going to solve this problem. All right. So let me go to the whiteboard here for a second. And Teams is located right here. Back to the whiteboard. So let's just do a notional thing. I go through and at T1, T2, T3, T4, and maybe over here at T5. And I'm not putting these equally spaced, although they may look at, the intent was for these not to be equally spaced, because I'm saying these aren't equally spaced points, but they wouldn't have the spacing when I look at this. But let's say I solve for my state x, and let's just do a scalar x as a function of time. I might get a solution here, and my NLP might say, yeah, you have something here, and you have something here, and you've got something here, and you've got something here, right? So that's what the NLP gave back. So what is the state trajectory? Is it something that looks like this and that with a discontinuity here? Probably not, right? Probably not something like that. What I would think it would be something like do the undo button. You know, maybe it looks, I would think it would be maybe more something like, oh, but what happens in between here, right? Right, when I do this, how do I know what's going on between T4 and T5? There's a big gap, okay? So maybe it does something like that. So you're right, these gaps, the question, how do I connect the dots? So I can find, so I need to figure out, one, where to place these points, okay, to get a good answer. And how do we measure good, right? So I need to figure out where to place these points, because evenly spaced points probably aren't the best way to do it. Then I get a state solution exactly at those points. But now I need to figure out, okay, so I got dots, I have dots now, how do I connect the dots, okay? So I need some type of interpolating polynomial, okay? And I will exactly satisfy my NLP at these points. And can you guess what these points would be called?
Are you going to use a Chebyshev polynomial for those
I could
points?
use exactly. I could use a Chebyshev polynomial. I could use a Legendre polynomial. What I want to do is I want to use an orthogonal polynomial. Exactly. Yeah. So that's really exciting. So we'll get ready for that next week. But these points themselves, they're going to be called our collocation points. Okay. And that's where we're going to exactly solve our NLP. And our NLP is going to be the approximation of the optimal control problem. So now I have that, and I have my control also at those points, okay? And then the question is, yeah, how do I go through these? How do I interpolate between those? In these methods, if you look at Matthew Kelly's paper, right, the DIY collocation, that's going to be using like cubic splines or B-splines or some type of spline fit here. When we do pseudo-spectrum methods, we're going to want to use an interpolating polynomial, and we would like an interpolating polynomial that makes sure that we are exact at these points. Okay, so that my interpolating polynomial doesn't do like something like this, right? With that, I want an interpolating polynomial that's going to give me my state as a function of time that is also exact at my points. Okay, so for those of you who had a class with, like, you know, Dr. Akers or any of the numerical methods, which is basically Dr. Akers, have you talked about interpolating polynomials that have certain properties that allow you to go right through the points you're interpolating?
So far, we've gone over the Chebyshev, and we've gone through Newton divided difference approximations.
Okay, yeah, so on this one, we're going to do Lagrange interpolating polynomials, okay? And so we'll talk more about that next week, right? And so the question is, and since we're talking about how do I actually find these? Well, those Chebyshev polynomials or Legendre polynomials, I want to take an orthogonal polynomial and I want to find the roots to that. And it's going to turn out the roots, putting my collocation points at the roots of that orthogonal polynomial is going to minimize some errors, right? That will identify those errors next week. And those aren't going to be evenly spaced. Okay, it's basically going to identify our errors in our quadrature for this. So that's why we call those direct orthogonal collocation methods. Okay, so hopefully we're kind of putting some words together here. Now, what have I done? Sorry. Okay, so we're doing these, right? We can do variable length phase durations. So now, if I had multiple phases, okay, now I could have where I have free final times in each of those phases. Like for the example where I launch from the ground, get to orbit a couple of times, and now get back to the ground. The times that each of those phases would begin and end are also the design variables. They're also unknowns in that problem. Okay, and including path constraints is much easier than shooting methods. And like we said here, the formative defect It's going to depend on the numerical integration scheme that you use. And fun fact, with direct collocation methods, you can do some math that you can show that, you write out your sequencing, you write out how you're doing your collocation. You can show as this h, or that distance, goes to 0, right? You can show relations between your Lagrange multipliers, right, from the NLP, and the co-states, right? And I think it's, I don't quote me on this one. I think it's with Hermite-Simpson, it's like Lagrange multipliers like 2/3 the co-state or something like that. You can find relations like that, okay? With pseudospectral methods, direct orthogonal collocation methods with certain properties, you can really relate them almost one-to-one, okay? And then there's a lot of math to back out what happens after that. But that's how you can get approximations for your co-states, and that really happens in the limit, right, of that step going to 0. So just some trade-offs between indirect and direct methods to kind of close out here. The calculus variations, right? We get insight into the structure of the problem. Okay, if we can get an analytical solution for arbitrary initial states and arbitrary final states, and we can express our control as a function of that, we have that problem solved. And we know how to get the control, we know how to get the co-state information, we know how to get state information. We can check we can check our optimality conditions, we can check our Hamiltonian, and we have a lot of insight into that problem. And if that's a problem that we're going to be solving a lot, it may be worthwhile to go through and solve that. When we go to, say, indirect numerical methods using indirect numerical methods, where we derive those necessary conditions and we try to solve a 2-point boundary value problem, the Hamiltonian boundary value problem. We talked about states and co-states, right? I'm going to be unstable in either backward or forward time, right? The states are going to be, if I have stable states for a linear system, stable states in forward time, co-states are unstable in forward time, right? Because I have the difference between my eigenvalues being positive, my eigenvalues being negative for stable, and since we minus A transpose, my eigenvalues would be positive for and giving me unstable. So they often, right, for the problems we want to solve, they are difficult, right, to derive. Generally, they're intractable, right, when we try to do that. But if we can get a solution, we get a solution, and that's wonderful. Direct methods do some type of finite differencing, right? And actually, pseudospectral methods originally came from trying to solve, i.e. global pseudospectral methods kind of came from trying to solve CFD problems and fluid dynamics problems. And it was around I think the late 80s, kind of like where they started applying these to the optimal control problems. Solution structure with a direct method, not as quite as easy to understand, right? We kind of get this for an initial state and for some given conditions for the problem. And we're not really sure how close we are to the actual truly satisfying the necessary conditions of optimality that we are, right? Because we're solving an approximation of the optimal control problem. But hey, it's pretty large convergence radii compared to the small convergence radii that you have over there with indirect numerical methods. The NLP, majority of the time, right, easier to solve than the boundary value problem, okay? And we didn't derive the optimality conditions, which again, for the problems that we're interested in, deriving those optimality conditions could be pretty hard to do, okay? So in reality, you might want something that gives you the best of both worlds, okay? You might want something that gives you the liberty to approximate the optimal control problem as an NLP, and is really robust and allows for a variety of solvers to try and solve that NLP. That allows you to incorporate terminal conditions, different events throughout, path constraints, multiple phases. But you would also like a little bit of information about the indirect method, so you can start to kind of assess optimality. And so now more on the state of the art, what you'll see now in numerical methods for optimal control. We'll look at pseudospectral methods for the first couple of days next week, and then Wednesday we'll do that tutorial on GPOPs, right, and build some of these from scratch, right? But we need to understand some of what's under the hood in GPOPs. You could take, a pseudospectral commercial solver and really just trying to figure out what the inputs and the outputs are, and that's completely fine, right? You know, there are people who do that, and that's completely fine, right? But then if you ask them, hey, how do you do that? What are you doing for your mesh refinement? It doesn't work out. It's not good responses, right? If you treat it as a black box, but you can, right? You can treat it like a black box and put something in and get something out. But we would really like to understand a little bit of what's going on inside of that. So that's what we'll do. First part of the week is we'll look at these pseudospectral methods. And first we'll try to figure out why they're called pseudospectral, right? So any questions or anything to talk about, or anybody just like crazy excited about next week and not having to drive optimality conditions anymore? And
I think I'm definitely excited about that.
Yeah.
Just don't know how easy moving forward will be.
yeah, okay, yeah. So I'll go ahead and so I'll stop recording now. And for that, so because that's the